Assalamualaikum. So here we are in the second part of ultraviolet visible spectrophotometry video. Okay. After you coggle up all the information in the active learning just now, okay, most of you understand at least the part that you did coggling. Okay, and now I'm going to collect everything and put it into pieces and make it like a bigger picture of the jigsaw puzzle, and to explain all of the parts, 9 of them, in this video. Okay, we start with the light sources. Okay, ideally we want a light source that can cover between 100 nanometer to 730 nanometer. Okay, this is ideally, whereby it can cover UV until visible. Okay, we have one light source that cater this ideal solution, but I want to go into the detail of the original light source and still being used until now because of the cheap cost, which is the deuterium or hydrogen lamp that can cover UV range. Okay, this is the one. While the one that can cover visible range is tungsten lamp. So tungsten lamp is the common tungsten lamp that been used in our surrounding nowadays. Okay, and also we can use iridescent lamp that can give the visible part. Okay, and then another one, we have a xenon arc lamp that can cover the same range as the tungsten lamp. Between tungsten lamp and xenon arc lamp will be more expensive because of the high energy needed to produce that radiation, but therefore it is more long lasting as compared to tungsten. Tungsten is usually using filament. Okay, so you can identify that it is actually having quite short lifespan as compared to xenon arc lamp. Okay, the one that can cover everything here is what we call as the hollow cathode lamp. The hollow cathode lamp is a line radiation source, whereas the xenon arc lamp, the deuterium lamp, as well as tungsten lamp, they are continuum light source. Means that in line light source, the energy being given out is continuous and never can reach like a gap during the radiation source. Okay, as compared to continuum, it can reach like one cycle, and then it can have like a pulse for a certain millisecond and then continue again. So in here, that's why it justify the short lifespan as compared to the hollow cathode lamp that is having line as the radiation source. So in terms of cost, of course, anything that can cover a lot of range is more expensive as compared to those in continuum. Okay. So if you see intensity versus wavelength between 200 to 900, this is what we call ideal, as the one from HCl can give, hollow cathode lamp can give. Okay, if let's say you use deuterium lamp, is between 200 to berapa tadi? 200 to 330 something. So it's between this until here only. So everything else is flat. So the D2 lamp, okay, deuterium lamp we call as D2 lamp. Okay, so it has a lifespan and also can give wavelength from 200 to 330, but the amount, the radiant flux is decreasing by each wavelength. So you can predict that if I want to analyze sample having that can absorb wavelength at 250 nanometer, is D2 lamp okay with me? So you see on the radiant flux is still okay. okay, as compared to 330. Usually at 330, the intensity is relatively lower than when you use shorter wavelength. So if let's say your sample can be detected at 2 wavelength between 250 and maybe 280. Okay, for example lah kalau ada kan. So you choose 250 as your primary wavelength for detection as compared to 280 because D2 lamp will give radiant flux lower at this wavelength as compared to 250. Okay, tungsten lamp pula. Tungsten lamp, the highest intensity for wavelength is the most optimum one is around 700 to 800. Okay, if you use around 4 to 500 is still okay. Okay, but irradiance is not as good as this one. Okay, and then we go to the second part, which is the wavelength selector, or we call it as monochromator if you are using spectrophotometer. This is where the identity of between you are using photometer ataupun spectrophotometer. Photometer senang je. You just remember if you use a filter as your filter optics, then you are using photometer. If you are using monochromator, okay, as your optics, then you are using spectrophotometer. Okay, when you that's why when you do chemical analysis next time, when you want to analyze things, you have to see should I use photometer or should I use spectrophotometer. Okay, all the advantage and disadvantage of each will be discussed later. But as for the purpose of discussion in this class, I will be talking a lot about spectrophotometer. So we will be discussing the most advantageous and also more complicated instruments so that we can use that instrument for various chemical analysis. Up until now, can you guess what are the difference are? Okay, so in terms of the difference between the technicality, it is using filter to select wavelength. Filter dia besar ni je, 25 mm je on the diameter. Okay, this is diameter. Okay, all for example, if you have a radiation source kat sini, radiation source, okay, and then your cuvette kat sini kan, so it goes into the filter. Filter only can each filter only can give you one wavelength. For example, if let's say this filter give you 300 nanometer wavelength, whatever comes out from here is only 300 nanometer. So from this white light, 300 nanometer je masuk, and then bombard your sample so that your sample can absorb and then go into the detector. Can only detect one single wavelength at one time. Okay, if let's say you want to test 310, you have to change the filter. So we have two types of filter, interference filter and absorption filter. And then on the other hand, monochromator is a set. Okay, dia adalah satu set. So kalau satu set means dalam dia ada few optics, okay, few filters and prism or grating. Okay, prism macam ni. Then we have optics. Okay, which is the entrance slit, exit slit. Okay, so your radiation source kat sini, and then it will select whatever you want lah. Okay, this is prism. Another one we have grating. Grating is like, okay, we have like a small parts and then it can diffract. Okay, it allow to scan various wavelength at one time. So this is very good for unknown sample. So whereby this photometer is good for QA QC routine monitoring because you already know what you are dealing with, right? Okay, so these are the radiation source can be continuous source or line source such as the hollow cathode lamp. So both monochromator or filter, there is only one reason, which is to isolate, to select, isolate means select the desired wavelength band so that the only wavelength is detected and measured. Okay, that's the reason of doing that. So I don't want to go a lot in terms of the absorption and interference filter. You can read on your own on this filter because I want to focus more on the monometer. Okay, filter, the best thing about this is low cost. Okay, low cost and also portable. That's why in most portable instrument they use filter because it's rugged and also stable and easy for maintenance. However, personally for me as a researcher, it is not going to give me a broad spectra. Okay, sebab dia only like one lambda at one time. Monochromator, okay, consists of entrance slit just now, entrance slit, and then you have either prism or grating, diffraction grating, and then you have exit slit. Okay, the prism over here, or the diffraction grating over here is what we call as dispersing device. Okay, to separate different wavelength. So after you separate the wavelength from the radiation source, you must want to have the exact 300 nanometer that you choose. So we have to have a focusing length. So the focus that is also giving you the same function as collimating lens, whereby it selects the specific one. Okay, exit slit to isolate the final wavelength. So this is the example. This is monochromator using prism. Okay, this is the prism, and then this is the collimating lens and focusing lens. You can go into the YouTube and then you can see how many animation on it, so that you can understand more on the this one, the wavelength that goes out. And then we have ini sama tadi. And then we have monochromator using diffraction grating. You see, it's grating. So grating is like your compact disc, CD kan, CD ke DVD, same. It contain a lot of like small teeth over here that if let's say you move this grating a bit left or a bit right, then all this angle changes. Semua changes. It changes according to the wavelength that you want. Okay, just like this. You see, monochromatic beam at incident level angle. Sorry. Okay, now we come to the part filter versus monochromator. Okay, filter. Okay, a lambda cannot be varied continuously, and lambda can be varied continuously. And also, this one is suitable for quantitative work only because we only have one filter. So QA, QC using one filter is good quantitative work. Whereas for monochromator in spectrophotometer, monochromator digunakan dalam spectrophotometer, okay, will enable you to do qualitative analysis because it scans the whole wavelength from the light source. Whereas for filter, you are using filter in a photometer. So when I give you test or quiz, okay, when I say UV VIS photometer or UV VIS spectrophotometer, you can now differentiate two of them. Okay. Okay, now we move towards the third part of our UV VIS spectroscopy instrument, which is the sample cell, the heart of the whole instrument, whereby it contains your analyte. You put your analyte inside cuvette, but which cuvette to be used? Okay, it's all depending on your sample. You can use quartz if you want to analyze something at UV region. Okay, if you have colored solutions such as food dye that possess wavelength more than 315 nanometer, then you can use glass cuvette and plastic cuvette, which is suitable for 300 and above. Okay, but if you use quartz, for example, if you use quartz for dye, boleh tak? Is it okay? Still okay, because it is also usable within this range. The second example, if I have a colorless solution, okay, having like wavelength around 254, for example, can I use plastic? Okay, the answer is no. You cannot use plastic because plastic absorb this wavelength. Okay, plastic absorb the wavelength at this range. That's why it's only good for 300 nanometer and above. What happens if your plastic or glass cuvette absorb the radiation at that wavelength? It will give you what we call as positive false. For example, if you want to analyze naphthalene, tapi you pergi guna silicate or plastic glass, and then suddenly you get absorbance of 0.899. Is this correct? No, this is not correct because it is false positive. Okay, your plastic cuvette is the one that is absorbing it. Okay, not your naphthalene. So when your plastic cuvette absorb the wavelength, means that what's left for naphthalene is less. Okay, it's less, and it added up to the equation at the VIS law. So path length is depending on your cuvette. Okay, the bigger cuvette you use, the bigger cuvette you use means that your B path length is bigger. Means that later you will have higher absorbance. Okay, but which one to be used? Okay, usually we choose 1 times 1 cm times 1 cm on the dimension. This is used for dilute sample. Okay, if we have a concentrated sample, you see that the path length is even smaller. Okay, kecil je. Okay, 0.2 cm. Okay. Okay, next, this is for doing chemical space. For example, if you want to do interaction study and so on. Okay, glass cell is usually used for CO2 or CH4 gases analysis, just like in inorganic analysis or inorganic work. Okay, so this schedule will help you to understand which cuvette you should use depending on the material. Precaution. Okay, since that cuvette give one function in VIS law, means that you have to take care of the cleanliness of the path length, as well as the means that you have to take care of the cuvette. The cuvette must be clean. Why? Because if you have fingerprints on them, your fingerprints can absorb the radiation. Instead of the one inside a cuvette, your fingerprints outside the cuvette can absorb. Okay, now we go to the solvent. Okay, selection of solvent. Why we have to discuss about this? Because your sample solution is usually dissolved in at least one solvent system. The minimum is dissolved in deionized water. Okay, so you have to know, is my deionized water absorbing the UV, the radiation that is given? is my methanol is absorbing as well, is my hexane is absorbing as well. So you have to understand. When you understand whether the solvent are absorbing, then you can choose your solvent better. Okay, for example, water will absorb UV radiation at 190 nanometer. This is not a problem, because most of the sample we analyze between 200 to 730 nanometer, right? So water is the most common solvent used in UV visible, means that the common solvent to prepare your solvent. To prepare your sample. Okay, what if you cannot use water? What if your sample is very hydrophobic? So you are thinking about hexane, kan? Hexane can help to dissolve polyaromatic hydrocarbon, for example. Still, it's not a problem, because the solvent cutoff, what we call as solvent cutoff, is still low, 200 nanometer. You want to analyze naphthalene, for example. Naphthalene, as the analyte, detected around 254. So kalau naphthalene 254, tak ada problem lah. And hexane will not interfere with the adsorbance at 254. If you are using, for example, apa benda? Chloroform, for example. Chloroform to analyze naphthalene, then you will have slight problem, because the wavelength is now small difference. Okay, small difference. Therefore, maybe chloroform will absorb certain part of the radiation before it goes to naphthalene. Okay, that's why you have to select your solvent very carefully. Okay, if you use toluene, of course cannot. Acetone lagi tak boleh. Okay, because it will absorb everything. That's why in research or in any analysis, we stick with water, methanol. Sometimes we have to use hexane, and sometimes we have to use acetonitrile. Okay, it's really rare to use acetone. It's really rare to use toluene because of the interference in terms of absorption. And then the last part is detector. Okay, the detector is even though it's the last component, is very important to be understood. We have single wavelength detection and we have full spectra detection. Okay, now where does this part important? If you are using photometer, for example, tadi photometer apa maksud dia? Photometer means dia use filter, means dia guna that can isolate one lambda at one time. So using PMT is the correct choice. Using diode is the correct choice. Can you use CCD? Yes, you can, but it's a waste of money. Okay, the same thing for diode array. It's not suitable to be used with photometer. Whereas if you are using spectrophotometer, okay, the one that can give you multiple wavelength, can you use PMT? The answer is yes, but you are doing something that is not bijak. Okay, because you have multiple lambda, but you give the instrument a single lambda detection. So you have to use diode array for this part, for this choice. Okay, so I summarize: single lambda detection is usually used for photometer, while for full spectral detection, CCD or diode array is used for spectrophotometer. Now let's go and understand what's inside. Okay, so photomultiplier tube simply means it multiply the photon. It multiply the photon. If you see from this diagram, it multiply. Biar detector detect, they detect high signal. Okay, you can read on your own here. Okay, this one the same thing. Diode array detector. This is the light coming from the grating monochromator. Remember the grating just now, it looks like this. It can give you a lot of radiation. So to receive all this radiated wavelength, you need to give the instrument diode array detector or CCD that have a lot of this channel over here to select and detect, and then you will get multiple peak. Okay, you can read on your own over here. This is the charge couple device. This is basically semiconductor device, okay, made up of sensor array over here, silicon wafer, everything. So this is the part. So it is actually charging uh, the couple device multiple times. So this is the summary of the detectors. Photon detectors is this one, the one that we discussed, while thermal detectors is used mostly for IR and far IR. Okay, so this is the UV visible spectrum. It has been shown before, whereby the y-axis is absorbance. It can be also transmittant. Kalau absorbent, you will get positive peak lah. Kalau transmittant, you will get negative peak. Okay, and the x-axis is wavelength. Okay, you see that different concentration will give different absorbance signal. Okay, the more concentrated it is, the higher the peak height. Okay, then you also coggle up about single beam and double beam. Okay, single beam spectrometer, it employ a single source, satu source je kat sini, to supply radiation to the sample and to the background. Bila kita nak buat UV visible analysis, we have to put reference cell. What is reference cell? Means that the same cuvette that you use for sample, but you put your blank. Okay, you put your blank because you don't want the instrument to read the previous analysis from different operator. For example, you want to make sure that the blank is having zero adsorbance, okay, so that your sample will give you the correct and accurate adsorbance data. Advantage is single set of component. However, the disadvantage is that it can take a lot of time for you to put one reference cell, bawa keluar, and then put sample pula, because it's only one line over here. So that's why it is not that popular in lab as compared to double beam spectrometer. Okay, double beam spectrometer, even though it's more complicated in terms of the optics, but it will enable fast analysis. Okay, still it is using one source, but it's split the radiation after it goes into monochromator in towards one to reference, towards sample, and then it will be detected over here. So this is very good for QC, QA, and also for research and development purpose as well, because it fasten the analysis. Okay, we discussed before about deviation from Beer's law. So this one I will go quite fast. Okay, we discussed about sample limitation. The more concentrated it is, you will get a non-linear and sometimes will drop. Okay, and then instrument, if you use light or optics that will that give you a lot of stray light, therefore detector can see a lot of light and give higher signal to noise ratio. Okay. Chemical deviation, so where most of it is when your concentration of sample changes, and also when your analyte dissociate or associate. Dissociate means that causing amount of analyte to be less. Okay, associate causing original analyte to be less as well. Okay, why? Because it associate with for example, if it react with solvent, it will produce something else, or if it reacts with the dirty residue on inside the cuvette, it will associate and also react and make a new compound. Therefore, you will have reduced amount for your correct analyte. Oh my god. Okay, so two different cells were used to measure the adsorbance of standard and real sample solution. Can this be allowed? So you can discuss with your friends and throw your answer inside WhatsApp group. Okay. Okay, now we go to the last part of UV visible spectrometry. UV vis usually is used, most of it in analysis of food coloring, because of the application for colored compounds, senang guna visible. With vitamins such as B12, okay, riboflavin, it is yellow in color, so it is straightforward. Fatty acid, analgesic tablet such as paracetamol, okay, paracetamol is colorless, so you can expect that the analysis is between 200 to 390 nanometer. Okay, protein is also colorless. Trace metal is trace metal for those at transition metal groups. Okay, the one that I said about the type of interaction in UV visible. Okay, this is acetaminophen. Acetaminophen is the active ingredient in Panadol. Okay, it give you the lambda max at around 243 nanometer. Sini 243, and it give you around 0.7. So what is this? Ada juga satu peak ni kan. So it mostly come from the solvent. If you use water, then water just now water pula. Methanol absorb at 200 nanometer, right? Therefore, this is methanol peak. Okay. So, because it is so far as compared to the acetaminophen, so you can quantitatively analyze acetaminophen peak independently from the methanol, no problem. Okay. And then we have catechins. Catechins extracted from the green tea leaf. It is having lambda max around 245 nanometer. Still in UV range. Okay. It contain conjugated double bond, and then we have oxochrome. Okay. So you can predict what kind of solvent they use here. Solvent ni cut off dia around 210 nanometer. I think it's hexane and above. Or maybe no. Ethanol, okay? This is the real example from PSM few years ago. She wanted to classify synthetic food color, so between azodine, anthraquinone, and triphenylmethane, to see what is the wavelength that arise from these compounds. Okay, the preparation of the food sample, because it's a jelly food sample, so you treat it as solid, okay, not liquid, the jelly. So in here she used acid and base to remove glucose, and then solution will filter up and make up to the mark with distilled water and measure using UV visible spectrometer. Okay, so you see this is standard. Dia run standard juga. Dia run standard. It give different absorbance level at different concentration. So it can be seen that this is linear, means that between 2 ppm to 12 ppm, the analysis can be done. If let's say you have a sample containing 5 ppm, then this calibration curve can be